Hello, everyone. In this and the next several lectures, uh, we will be tying together many elements of the course by exploring an example of a machine learning project. Additionally, we will be exploring ideas like project management, version control, and working in a Unix type environment. I'll discuss all these topics in more detail as we encounter them. But first, let me explain what I intend to do. So I'm navigating to Kaggle.com. Kaggle is a machine learning competition website. Kaggle hosts a rotating collection of data science competitions with cash prizes. The competitions are quite challenging. The winners are usually very experienced, not only as data scientists, but specifically with respect to Kaggle competitions. But even though the cash prizes might be out of reach, something that's nice about Kaggle competitions is you are given a well-defined problem statement as well as a data set. So one of the best ways to practice data science is to engage in an independent project. But coming up with a viable project can be very difficult when you're new to the field. You don't know where to find data, you don't know what kind of data might actually be easy to analyze or interesting to analyze, and it can be difficult to identify problems and data sets to actually get any practice in with. Kaggle sort of hands that to you in the form of their competitions. Not only that, but they additionally have a active community centered around the website. Each competition has its own discussion board where people analyze the problem and talk about what techniques they're applying. Additionally, the site hosts a number of data sets that are submitted by users that you can use to explore outside of just the competitions, and a number of kernels which are similar to Jupyter notebooks. Some of these will be written in Python, some of them are written in R, but what they have in common is these are all typically some mix of code and text and images, similar to the Jupyter notebooks we use to teach the class. They are executable, and additionally you can fork them, meaning make a copy of them and add your own work to them. So as you can see, this looks pretty similar to a Jupyter notebook. So that's Kaggle, and we're going to take a Kaggle competition as the starting point for the next couple lectures. So there's quite a few challenges on Kaggle that have some time limit. So some of these are like 3 months to go, 21 days to go, 9 days to go. And these are typically competitions that are have cash prizes, are sponsored by companies or institutions, and are some of the active venues or arenas where data scientists measure their skills against each other. But there's also a number of competitions marked getting started, which are meant for newcomers to the site to acquaint themselves with how the site works, and also, dip their toes in a machine learning project. So one of the classic ones is this Titanic data set. So the Titanic, of course, was an ocean liner that crashed into an iceberg in 1912, resulting in a tragedy where over 1,000 people died. And our machine learning task is to analyze data about the various passengers on the ship and come up with a model that can predict who would survive and who would perish. So that's the goal, to create a model that can predict who would survive the Titanic sinking. We are given a training set and a test set. The training set will include which of these passengers survived and which did not. And the test set has all the kind of demographic information or passenger identifying information, but it does not have the target labels as to whether or not that passenger survived. So let's download these. And I have to log in. So I believe this is attached to my Google account. So now I'm logged in. Go ahead and download the data. Test set, training set, and let's see here. I'll just make a new notebook right here. And we'll upload these data sets. And we'll call this Titanic. We'll give that, we'll make that the name of the IPython notebook. So let's start by exploring the data. So we'll read in the data sets. And first off, we notice, as I mentioned, the training set has this survived column, which is not present in the test set. We're trying to predict whether or not people survived, so it makes sense that we only have these labels for the training set, not the test set. So first thing I'll do is I will take the training set and I will pop out this survived column into a variable called y, since that's our target labels, and the remaining portion of the data I will call x to indicate that this is the feature matrix. So now x only has the variables that we will use to make our predictions, whereas y is just zeros and ones indicating whether or not an individual passenger survived. So let's begin figuring out what this data set means. So there's documentation on Kaggle detailing what the different variables mean, but before we look at that, let's just see what we could figure out ourselves. There's a passenger ID, which appears to just be a label, 1 through the number of passengers. Not interesting, really. Probably not significant. This is just an enumeration of the rows. So this first one's not going to be useful to us. We have name, sex, age. These are all self-explanatory. Fare, how much a passenger paid to board. Some code indicating where they boarded the ship. Some kind of code relating to their cabin, where they stayed on the ship. This could be, for instance, what deck, and then maybe their room number. Some code associated with their ticket. It's not really clear what these things necessarily mean. We have these two mysteriously named features. I don't really know what these are just looking at them. And P class. Also not super clear, but could be a marker for what class the passenger was a part of. Maybe relating to where they stayed on the ship or something like that. So let's have a look at the data dictionary to resolve any outstanding ambiguities, which are this P class variable, sibsp, and parch. Okay, so P class refers to ticket class. So there are 3 classes of tickets. First class is probably where the most expensive, are probably associated with the most expensive tickets. Second, somewhat less expensive. Third, least expensive. That would be my guess. This sib variable is the number of siblings or spouses aboard the Titanic. So, husbands and wives, brothers and sisters. Parch is number of parents and children. So these are 2 variables kind of representing familial relationships. Also detailed are what some of the codes mean. For instance, what these embarked codes mean. So someone who is marked C boarded at Cherbourg, someone marked Q boarded at Queenstown, and S passengers boarded at Southampton. So now we know what all these things mean. let's continue exploring. Are we missing any data? This is always an important question to ask ourselves. So we can check that with the isNull method, which will give us true or false depending on whether or not there are missing values. We can sum up the number of trues for each column, and that will tell us the number of missing values in each column. So we have data for most of the columns. We have some missing values for age, embarked, and cabin. Now keep in mind, any scikit-learn estimator, well, not any, but most of them will not be able to deal with missing data. So we will need to somehow deal with these missing values, either by filling them in with values or by removing the column from the data set. So how do we make that decision? Well, first of all, it could be useful to not just have raw counts here, but a percentage of how many rows out of the entire data set are missing data. So age, we're missing about 20% of the ages. Embarked, we're missing less than 1% of the data. And cabin, we're missing almost all of the data, over 3/4. So with so much missing data for the cabin feature, we will probably not be able to meaningfully reconstruct this missing data. So much of the data is missing that what remains is maybe not so useful. If we tried to fill in values, we might make up patterns that don't actually mean anything and that weren't really present in the original data. So cabin we'll just remove. So we no longer have cabin in the data set. Embarked, very little of the data is missing. In fact, earlier we saw it was only 2 records, 2 observations. And so we can fill these in with pretty much whatever we want. Whatever we put here for just 2 of the observations is probably not going to make a very big difference either way. There are 3 options, S, C, and Q. And probably what will be most reasonable is just to put the most common values in these 2 slots, these 2 rows. So if we look at the embarked column, S is by far the most common value for embarked. So we'll just take embarked, fill NA with the fill value S. And we'll just set the embarked column to be equal to this result. So now, if we look at the number of null values, we eliminated column, or cabin, so that doesn't show up in our result anymore at all. We also filled in the null values for embarked. So now we only have missing data for age. There are a number of things we could do here. First of all, let's get a feeling for what the distribution of ages was across these passengers, and also how it relates to whether or not they survived. So, most of the passengers were between, say, 20 and 40 years old. It strongly peaked around the mid-20s, and and it's not so heavily skewed in either direction. Um, we could fill in these values with the mean. The mean will probably be, about here. So X age mean, 29 years old. So right around here. The median age was 28. So this data is slightly skewed to the right. Median will be less sensitive to that skewness than mean is. It's not necessarily easy to know in advance which would be a better choice here. There are more sophisticated choices we could make. For instance, we could look at how age relates to whether or not people survived, or ticket class, or other information that we do have, and try to reconstruct age based on other variables. So, for example, if we group our data frame by class, take age, and take a histogram, okay, this isn't doing quite what I want. Let's try Seaborn. So Seaborn is a data visualization library like matplotlib that plays very nicely with pandas data frames. Often we're able to give it things like group bys, and it will use that group by to organize the data. However, I don't quite remember the syntax, so I am having to look it up. No shame in that. It's a very common thing to do. All these different libraries have different methods, different keywords for each one. And so often, rather than being able, I can't remember them all. And so often I am Googling to remind myself what keywords are allowed. My recollection was that group by is possible with Seaborn. And in fact, there is this Stack Overflow post indicating that it is possible. But keep in mind, these libraries are always under development, and it's possible that this post is referring to a different version than the one we are currently running. So let's try this back in pandas again. X group by P class age hist. So this is fine, but I can't see the orange and the blue histograms very clearly. So what I want to do is give this hist method a transparency argument. And normally I would be able to do this with alpha. And this would modify the transparency, but it doesn't appear to be working, and I'm not sure why. So I'll do this in a slightly less elegant way. I will iterate over the unique values of P class. I will select out where the P class is the current value. And then I'll plot this as a kernel density estimator plot. So class 1, that's the upper class, tends to skew higher in age than the lower classes 2 and 3. So what we might do is, in fact, calculate since the distribution ages is slightly different for the classes, what we'll do is we will calculate a let's do a mean age for each class, and we will use these different values to fill in the missing values in our data frame by filling in the missing ages based on what class that passenger is. And this will use some information we do have to fill in information that we don't have. So here we have the same expression that we used here to calculate the missing ages for each type of class. Here we select out the portion of our data frame for classes 1, 2, and 3. Those 1, 2, and 3 values will be in this P class iterating variable. And so we're just setting all the records that have class 1 or 2 or 3 to their appropriate ages that we calculated here. So finally, now if we do x is null, sum, we have filled in or gotten rid of all the missing data. So we no longer have any missing data. Terrific. So now our data is kind of clean. We could begin doing machine learning right now. However, first of all, we don't have any idea how any of these variables relate to our target label. So we should first explore the data and assess which variables are important, which variables are probably unimportant, and whether or not we might be able to do any transformations on our data to represent what information we do have in a way that could be more useful to a model. Additionally, we've just hit kind of a milestone, and it might be nice to start organizing our work and managing this as a project and check in our work to version control. So I said a bunch of words just now that may or may not be familiar to you. Let's begin with version control. So you may be familiar with the experience of collaborating with others to write a paper. So you're writing a document together with someone else, and you start writing, and you write, Jack and Jill ran up the hill. And you're ready to start telling the story about Jack and Jill running up the hill. And you go on to say, at the top, they found a well. But in the meantime, your collaborator has changed up to down. And now, the phrase, at the top, no longer makes sense. And it's not clear if the line you added here should take, where we presume that Jack and Jill ran up the hill, should take precedence over the change your collaborator made in the meantime, that they ran down the hill. This is where version control comes into play. Version control is a system for recording changes to files so that we can detect and resolve conflicts in edit history. So, for example, if you began Jack and Jill ran up the hill, you could check this into version control. Now, your collaborator, unbeknownst to you, changes it to they ran down the hill. And that your collaborator checks that into version control. You don't know this because you're somewhere else, still working on this document. And you write at the top, they found a well. Now, when you go to check this into version control, your copy will say up the hill and top, but the version that your collaborator has says down. And so the version control software will say, hey, we've encountered a conflict. Your copy says up, but their copy says down, and you two should get together and resolve this conflict. This can be very useful when dealing with code, where these kinds of changes the functionality of our program, and it can be very difficult to keep track of changes in, files of code that may have hundreds or thousands or tens of thousands of lines. So one of the most popular version control systems for code right now is called Git. And there's additionally a online sort of tool for storing code and collaborating with others using Git. And it's called GitHub. So here's my profile on GitHub. I have several repositories. These are directories where there is code that I have worked on. In some cases, this is code that I have written myself, and I am the sole contributor. So here is a name generator for names from all around the world. I am the only person that has contributed code to this repository. It consists of a text file saying what Python packages you need in order to run this code, and a Python script, it's very short, that actually will generate the names. I also have repositories where I have collaborated with others. For example, this repository here says that I forked it from another repository. That means I made a copy where I made changes, and then I submitted those changes back to the original project for incorporation into the official repository where this tool is being developed. So this has quite a few files. We see several Python scripts. And there are more contributors, more than just me. So here I am. I made a very small contribution, 6 additional lines of code, and 3 deletions. So how do we use Git and GitHub to start reorganizing our project? Well, this is something I can show you how to do, but your environment for the course is not quite set up to do it. I am instead going to show you how to use Git rather than in the Jupyter Hub environment. I'm going to show you on my Linux workstation. So I use an operating system called Linux, which is based on Unix, or it's a derivative of Unix. Mac OS is also a derivative of Unix. Windows is not. However, the latest version of Windows, Windows 10, includes a Linux subsystem. And I highly recommend that if you are using Windows, you explore using the Linux subsystem. Being familiar with Unix-based operating systems like Mac OS and Linux, and being comfortable with working on the command line is a core skill for most data science positions. And there are tutorials on using the command line. One that I particularly like, or a site that I particularly like for these tutorials, is Ryan's tutorials. He has a Linux tutorial, a Bash scripting tutorial, and these will introduce you to these kind of tools and environment I am about to show you. So, this is my computer. Here are some of the things in my documents folder, and I'm going to make a new directory called Titanic. And I will enter that directory using the cd command. I don't expect you to follow all the commands that I'm using to interact with the command line here, but I just want to illustrate how this typically works, and you can have a look at this Bash tutorial or this Linux tutorial if you have access to a Linux or Unix-based workstation, and you can explore some of this yourself. But right now, I mostly want to illustrate a picture of how this works. So on my machine, there is this program Git. So if I just type Git and hit enter, it shows me this help information that tells me how to use the program, some common commands, what they do. So there's a section here, starting a working area. So I want to start a new project that I am going to version control using Git. So I will use this git init command to initialize the project repository. And when I do git init and hit enter, it tells me initialized empty git repository in the address where I am, documents/Titanic.git. And indeed, there is now a Git folder in this directory, which has all kinds of little files Git uses to help keep track of changes to any files in this repository. Now, I can hook this up to a repository on GitHub. For now, I'm not going to do that, but we will explore that later. For now, I just want to start actually putting things in this repository and adding them to version control so that if we ever mess up in the future, we have kind of a copy checked in that we can revert back to and know that our project was in a good working state at that time. So currently, I have on my Jupyter Hub this IPython notebook where I've been doing some exploration. And this is fine, but we only really did, a lot of what we did here was just giving us information about the data set. We were just exploring. And we don't necessarily want to replicate all that work every time we want to make some predictions about who would survive from the Titanic. What we really need to do is just prepare our training data. That's all we've done so far in terms of progress in the project. other than improving our own understanding of the data. So let's extract from this notebook the parts of the lines of code that actually prepare the training data for use in a model. So I'm going to create a Python script called Titanic.py. This ampersand just says to run this Emacs program in the background. Emacs is the name of my text editor. So when we launch this, we just get a little text editor where I can type text and have it show up. So I'm not sure that I can actually zoom into this. I've never tried to zoom in. Will this do it? No, that's search. Okay, so now this is showing up nice and big. So I'm going to use pandas. So I'll first import that. And one of the first things I want to do is read in my training data. I'm going to hold off on splitting this up for now into X and Y. I'm also going to skip loading in the test data for now. So here we were inspecting, what are the null values, and this is really where we start to get into what we did to the data. So we dropped the cabin column. We filled in the missing values in the embarked column with S. And we filled in the missing age data. So this will read in our training data, remove the cabin column, fill in the missing values in embarked, and fill in the missing values in age. And so far, this is really what we've done in terms of cleaning up our data. So I've saved this file. It shows up in our directory as Titanic.py. And it's time to, you don't need to worry about that, that's just for me. It's time to check in this file in its current state as like a checkpoint in our project. We know that this works well. We tested it in the IPython notebook, and we want to, sort of document our progress and create a checkpoint for what we've done. So we will add this file to what's called the staging area. So let me remove this actually just for a moment. So if we do git status, it tells us there are untracked files, meaning there are files in the repository that are not currently checked in to our version control. It's not checked into Git. So we will add these to staging. And now git status tells us there are changes to be committed, meaning Git is now aware of the file titanic.py, and it's aware that this file has changed. Before it didn't exist, so it tells us it's a new file. And it's telling us we can commit these changes. Committing a change is where we really record the changes in the edit history of our project. So we'll do git commit, and we'll include a little message that says what we did. So first commit, clean up training data. So now if we do git status, it tells us nothing to commit, working directory clean. We can do git log, and it tells us that we made one commit. And it shows us the message about what that commit is about. So what did I gain here? Well, I have my titanic.py file. Let's say I do something stupid. I remove this file. It's gone. But if I do git status, it tells me that this file is not really gone. Git has detected a change, that I deleted this titanic.py file, but I haven't committed that change. As far as the file system is concerned, as far as Linux is concerned, this file is gone. But Git remembers the history, and so it can reconstruct the file based on what it remembers. So if I do git checkout titanic.py and then ls, that file is back now. And Git not only allows us to bring back files from deletion, but even is more granularly aware of changes to individual lines of code, so we can revert small edits to files or large edits to files line by line as we or our collaborators further develop the project. In the next lecture, I will continue this project. We'll discuss a little bit more about how to organize projects, write Python scripts that are geared towards production, meaning are ready to be used in applications or as applications, and further delve into this particular Titanic machine learning challenge.